for nice introduction. This is Anthony from Caltech. Thanks all for the organizers for making this lovely events, and thanks you all for being here this morning. I'll be talking about a line of work that's still rapidly changing. We hope only put out one related paper yet, but more is going to come. So let's now enjoy Gibbs sampling. Okay. And before I begin, I'll ask the audience. So, how many of you have done a physics experiment before? That's quite a lot. How much of you identify yourself as physicists? Okay, I think that's what I expected. So the reason why I'm asking is because this topic is really between physics and computer science. There are lots of basically the same idea, but it was spoken in a very different language, and hopefully to bridge the gap between these two very different communities. And partly, I believe the reason why this topic has been kind of almost ignored for a long time is because the community haven't really quite talked together. Okay. So let's get started. The main task of interest is quantum Gibbs sampling. So you're given a quantum Hamiltonian and a quantum computer, fully fault tolerant, and your task is to prepare the Gibbs state on your quantum memory. This is perfectly well defined. The Gibbs state here, it's a quantum states that's a incoherent mixture of the energy basis states. They are weighted according to the Boltzmann weight, which is exponential minus beta e. For who are more familiar with physics, this is something that people talk about every day. But even if you're from computer science, this is something you can write down and then start reasoning about this object. To get a more sense of what this is doing, if you make beta really large, so you see this exponential is going to be very small, it means that you kill all excited states, so you're basically in a ground state. And if beta is 0, it means that you kind of treat all the energies equally. You end up getting a maximally mixed state. Should be no surprise here. So now we already defined a problem, then we can just move on and discuss as a theorist the difficulty or some algorithm to achieve this task. However, I know there's some industry activity around quantum computing, so I want to give a motivation from those people here. So apparently, if you ask your industry colleagues or people who are now actively trying to build a quantum computer, they're looking for a killer app. Okay, this will keep their funding going. It also make them earn money. And the thing that seems closest, maybe not everyone agree, but it seems lots of people would think, is to do quantum simulation. At least that's my exposure. And so quantum simulation is a fairly well-defined task. We all know it's pretty useful because we have been doing simulation of quantum system every day. Mainly now is through classical computers. But now you want to do it in a quantum computer because everything is quantum, and use a quantum computer supposedly to be a very nice thing to do. Example usage could be, for example, to understand the ground energy of some molecule. You can put any molecule here. This molecule got to have some Hamiltonian, and you can just put that into your quantum computer. You want to understand its properties. Okay. And people, this quantum simulation problem have been conceived for a very long time. There are lots of progress, perhaps the most mature field in quantum algorithms. And you can imagine there are several things you might need to do. You might need to prepare the initial states, in this case, the ground state, or in many cases, the thermal states. You better want to know how to do this Hamiltonian simulation, and then do some measurements. Okay, and you can use all these things in all kinds of combinations, but this is basically the building blocks. And as of today, people are still very boggled by the first one, state preparation. To be very practical, if you look at this paper put out by companies, I might be missing out some of them. This is like a few years ago. The state preparation part has been a big mystery. So we don't know how expensive this one is. And this constant factor could just kill the whole industry. Right? If the constant is 1 million, then, well, it's not likely you're going to run it. Oh, like how expensive this task is. So there's just like some unknown factor, I think, called delta. And the delta, we don't know how big it is. Like the algorithm depends on the unknown factor. how expensive this task is.
So which algorithm are you talking about?
I suppose you want to achieve that task.
But there are various algorithms to do state preparation.
Yes, but for big molecules, it's not very clear how expensive that is. For a simple one, kind of know what's happening, but for bigger ones that you actually care, it's not clear. All good? Okay, so what's interesting here is that the state preparation problem is actually almost at heart of quantum computation. There are lots of various rich landscape and theory that's coming out of this. So let me now just ask, as a computer scientist, how hard is it to prepare low energy states? Right. So your gut feeling from complexity is that this problem seems really, really difficult. In the worst case, this is lies in this complexity class QMA. It's or at least as hard as that. And this is not a good thing to tell your investor, right? If you say, well, hell, we're going to build a quantum computer to solve this problem that our computer cannot solve. So this is kind of pessimistic. However, if you now ask different disciplines, people from different disciplines, such as computational people, they would say that, well, actually, this task could be quite easy. There are lots of people implementing highly efficient heuristic classical algorithms that solve chemistry problems, material science problems. It seems to work very well.
So the hardness of the QMA hardness is really if you care about more and more digits in accuracy, but as physicists, we don't care about having more and more digits. We care about having some accuracy. So is it wrong what complexity is?
Right. So for constant accuracy, I think still not very clear. But I think indeed, if you increase precision, it does get harder. I think people do get that. I think some paper have discussed that. But for constant precision, I don't think it's so clear yet. But it definitely gets easier if you don't want things to be so precise. Okay. Also, you see that on the landscape, there's two kind of bad things happening. Either the problem just gets too hard, even for quantum computers, or it gets too easy that even classical computer can solve it.
Maybe it's worth to mention, if the Hamiltonian is gap and you can implement it, then it suffices to prepare a state which just has a constant projection on the state.
Yes.
And then you perform phase estimation with a small precision,
exactly.
And then you get the graph state. So,
exactly.
so basically, to Fran's question, if the Hamiltonian is gap, this is the approximation could be very bad, and still it's hard as preparing the graph state.
Mm-hmm. Yeah.
One of them QMA hard Hamiltonians and one of them polygam.
Yeah.
So let's just keep going. So to make the story continue, okay, so what we want to do here is to find something here. Something that's quantumly easy and classically hard. That's kind of what we want. Right? And does anyone has a candidate Hamiltonian that fits into this part?
SYK?
Oh, maybe. I think that's like.
You could take Hamiltonians which you code the quantum computation. That should be quantumly easy to prepare and classically hard.
But yeah, I think you believe you can look up lots of
construction and run it on.
Yeah, so constructively, I believe yes. But are those problems that you want to run in your quantum computer and sell it to your customers? Anyway, so yeah, so in fine-tuning examples, I believe you can embed even BQP into here. But are there kind of more physically reasonable Hamiltonian that have this property? Maybe it's SYK model, or maybe something else.
When you say classically hard, you mean not prepare the state, but sample from it?
Right, do something out of state. So now I have been pretty ambiguous, so just think about preparing states. Right, so yeah, you see that there's two things that you want to satisfy. Both of them are pretty difficult. Hardness is always hard to prove, as we know. But if you want to prove quantum easiness, it's actually not impossible, because all you need to do is to give an algorithm and say that it works. Then you very concretely know you solved the problem, at least for quantum easiness. And that's what the route we're going to do today, is to think about new algorithms that potentially will lead to a lot of cases of quantumly easy low energy problems. To make the story continue, I'm going to ask physicists the same question. So ask your industry or your lab colleagues, how hard is it to prepare low energy states in your lab? But this is what they're going to tell you. They're just going to show you their dilution fridge and say that I do this every day. Right? So physics or thermodynamics just tells you, if you just couple your system to a bath, no matter what material it is, if you just put it in your bath, you push the button, then you get a Gibbs states, or sometimes you get a ground states. So it seems that if this is true, then we have a very strong kind of empirical evidence that lots of states got to be quantumly easy, right? Because nature or these baths got to be quantum mechanical. If you simulate the whole thing, you can prepare the Gibbs state. It is all heuristic, but I would like to use this as just like an empirical justification or the motif of this talk. Because what we're going to do today is to extract the essence of this phenomena and to cook up the quantum algorithm that captures this effect. What we're going to do today is to propose an algorithm that captures the previous slide. I don't have a good name for the algorithm yet. I just call it Monte Carlo quantum algorithms. The algorithm you're about to see will be very closely related or have been inspired by the idea of cooling and physics. I will not actually talk about any physical things here, because I guess you guys don't care about this part. But what's interesting here is that we have like an almost complementary, almost a view of the same subject from classical Monte Carlo. So for computer scientists, you can understand the algorithm of interest today. It's a quantum version of classical Monte Carlo. Surprisingly, the things is not existing. So we kind of present kind of the missing algorithm in the quantum world. Historically, classical Monte Carlo has been extremely useful. It's very simple to use, at the same time very robust. You can apply to all the cases you want. Initially, it started out being a physics simulation algorithms. People use it to study icing models. But then, throughout the past decades, it has evolved into like an all-powerful algorithm. I can apply it to optimization, constraint satisfying problems, machine learning, all sorts of stuff. And here, I just want to use this kind of usefulness of Monte Carlo to argue that the thing we're going to talk about today could likely inherit lots of the properties.
There's this paper of quantum Metropolis algorithm. I mean, it's basically something along those lines. So how does this compare?
Yes. We revisit the same topic. We recently realized there's some assumption that seems questionable, and we can in contact with them. So they could be both. And we also redo the whole thing completely. Yeah. So I'll talk about some of the reason why we redo the whole thing again. Right, so to begin, to set our stage for the quantum version, start with the classical one. This is all textbook material, I'll just very quickly review it. Markov chain Monte Carlo, often called MCMC, is the following idea. You want to implement a Markov chain, it's a stochastic matrix, such that if you repeatedly invoke it, you take product of it, converges to the Gibbs state. In particular, here's a checklist you want to go through to make sure that it's actually working. So first, it must be efficiently implementable. You want to efficiently implement this matrix M on your randomized algorithm. And second, you want the Gibbs state to be stationary. So it's the fixed point of this matrix. And with the first two, you can already run this algorithm and just wait how long. But you might not know how long it's going to converge, but you can wait, and can wait long enough, maybe it works.
Do you want that the Gibbs state is the only stationary state, or?
Not necessarily.
No. Oh, okay. Because usually people do kind of want it a lot.
Right, so it depends on what you want. If you really want a Gibbs state, it better be the unique one. Otherwise, you might get stuck in somewhere else. Sometimes you only care about low energy states. It doesn't quite matter. You just kind of want to get a sense of the landscape.
I guess probably the answer is it's coming in later slides, but what do you mean precisely by converging rapidly?
All right, you can make it very formal. It's like you can take the trace distance, and if the iteration L is, it doesn't require too many iterations for it to be close to the
But
Gibbs
it
state.
depends then on the, temperature, because this we know has to take exponential time for that sufficiently low temperature.
Yes, yes. So the mixing time could change a lot, and depends on all sorts of things.
So converging rapidly means cost per step, and then there's this unknown mixing time factor that could be exponential.
Yeah, if mixing time is short enough, you can say it's logarithmic or polynomial. You can also say it's convertible. And indeed, if you put some very hard problem in it, like given a hard problem, I mean, in this case, NP hard problems, it better not mix.
Do you assume something? I'm still lost in this argument question. Because I mean, if you have more stationary states, there's no guarantee that all of them will have low energy. Or you could have very high energy islands of station.
You could.
So you don't care about that, or?
Well, this is in some sense, a heuristic algorithm. That, I mean, you run it and you see how well it works.
But if you talk to Monte Carlo people, ergodicity is a core thing, right? And if you can't prove ergodicity, you don't need to lie. Yes, it's something very simple to check.
Oh, I see. Yeah. So here I just kind of throw away those things, but indeed, you want to design a Markov chain such that if possible, if you want to Gibbs state, you want to avoid those as much as possible. Okay. And if you design a Markov chain rapidly, then those things would occur. I did that discussion.
How important is reversibility? Are you interested in reversibility?
It's a very convenient way to get the Gibbs state. Like detailed balance, it's very convenient to get the Gibbs state. But it's not the only one. But I think a lot of case, because it's much understandable, people like to use. Okay, so let me just give a very quick example of what it looks like. If you have a 1D chain, there's like there's four different states. And let's try to design a Markov chain that converges the Gibbs state on these four states. Okay, so you can draw a Gibbs state. It's going to be exponential following distribution, right? Exponential minus e. And you can check that. Look at if you pick your transition rates exactly at these numbers, it does fix the Gibbs state. We can ask, like, if I want to go beyond this very simple example, how do I design my Markov chain without first solving the whole problem? Yeah, so how do you do it? So let's illustrate from this simple model. There's this idea called detailed balance. That is a very nice ansatz that give you stationary state as the Gibbs state. This ansatz, it doesn't always hold, but in many cases, if you're designing it, it's good to have it. Convenient. So the idea of detailed balance is to enforce that the flow between any two configurations cancels out each other at stationarity. Okay, so you can pictorially kind of see what's going on here. You can write down some algebraic expression that captures this thing. So indeed, if the two flows are equal, then nothing changes. So Gibbs state must be stationary. To reiterate, you can write it in the picture of transition matrix. Right? And this 1D line, the transition matrix is some tridiagonal matrix. And detailed balance in this case just amounts to the symmetry of this matrix. Right? So you're going to look at these entries here across the diagonal, and you want them to satisfy this algebraic ratio. This is just some number that depends on the temperature feedback. For example, if beta is 0, then these two are the same, so the matrix is symmetric. This exactly corresponds to the reversible Markov chain. If beta is large, then this is kind of biased, and it's not exactly symmetric, but they still obey some symmetry up to this factor. Okay. And now you ask, this detailed balance seems to be a very delicate condition. How are you going to implement it algorithmically? Right? Because you might start out with some huge configuration space that you don't a priori know what it looks like. And how are you going to implement detailed balance efficiently? But there is a solution, a very nice idea called rejection sampling that kind of is what enables Monte Carlo. Which is an algorithmic way to implement detailed balance without knowing the full matrix. So roughly, it's just implement detailed balance on the go. It's not like you first write down the whole matrix and then do something with it. It's just that whenever you see an entry, do some algorithm, and then it gets detailed balance. Okay, so what it's doing here is that you start with a symmetric Markov chain, and then you just decided that you're going to reject anything that occurs that's on this lower triangle. So you're just going to try to bias the flows. And just by sometimes rejecting one side of the move, you can kind of kill the transition here. And then it just becomes weaker. And then if you pick it correctly, you get detailed balance. So let's just look at an example with a very old algorithm called Metropolis Hasting and still being run today. Or there are lots of variants, but this one has kind of captured the essence. As a user, here are several things you want to specify. You want to choose a Hamiltonian, some inverse temperature beta, and some set of jumps. Right, this Hamiltonian could be an Ising model. There are some parameters. You just put it in your computer. And the set of jumps could be spin flips. So it's going to change the spin variable at each of your lattice sites. And these are all the parameters you need to fit into your computer. And here's what the algorithm looks like. You can start with some initial states, some spin configuration. And then you can randomly flip a spin. And the energy could increase or decrease. And when it decreases, that's good because you want low energy states. You accept the move. If energy increases, that's bad. And sometimes you have to reject the move. Okay. And then you have to reject it by undoing the jump. So whatever you did, you just have to undo it. Kind of pretend nothing has happened. And just by doing this, actually gives you the Markov chain. If you iterate this a few times, you actually get the Gibbs state if you converge quickly. Okay. So now let's just quickly summarize what we have been discussing. For the classical case, it will be useful to understand what are we quantizing. On the left, you have the choice of configuration, which are just classical spins. The Gibbs state is a distribution on the classical spins. It could be a classical Hamiltonian and some set of jumps. And what we want to do today is to make everything quantum. And here are some nice suggestions. I can upgrade the spins to entangled states. These are configurations. The Gibbs state now becomes quantum. The Hamiltonian better be non-commuting. Right, so this could be Pauli x and y's, which don't commute. And then now your jumps, since you're on qubits, you can have x, y, z's. Pretty intuitive. And the goal for today is to address this question. Right? How do we design an algorithm that quantizes this classical Gibbs sampling algorithms?
For an algorithm, does it matter the specific Hamiltonian to pick, or is it for more general Hamiltonians?
Oh, right. So this one is an example. So yeah, this should be a black box.
Do you require your jump operator to be unitary?
No. No, it doesn't have to. Yeah.
But you do require that it takes you from a negative to negative.
That could be arbitrary operator.
So you don't require that it takes you to a negative state.
No, it's arbitrary. Arbitrary. All right, so let's move on to the main course of today. Is how we design these Monte Carlo quantum algorithms. So one thing you might want to do is to just go to the energy basis. All right, so if you look at the Gibbs states and see how they differ between classical and quantum, classical Gibbs state is a probability distribution over the strings. The quantum one is just the same distribution, but on the quantum states. So intuitively, you might say, well, I'll just upgrade these bit strings to energy eigenstates. And just run Metropolis on these eigenstates, whatever that means. All right, so then if you just follow this line of thoughts, you would upgrade your transition probability, which is this matrix we have been discussing, and you want to upgrade it to transition amplitudes. Right, it's amplitudes because it's quantum. But what it means here is just to take the jump operator A and then sandwich with different energy eigenstates. And then you square it to get the probability.
But does that have the rejection in it then as well?
You have to, yeah, that's another thing too, yeah. But this is just the first step.
So should I think of the A's as Gauss operators of a CP that you apply as one?
Well, yeah, it will, yeah. So A is kind of like the bare, like the minimum thing you do. But then to get an actual cross operator, you have to kind of modify them. So because arbitrary choice of A is not going to have detailed balance. So you have to do some rejection. Like you have to modify them so that it becomes like a detailed balance.
So you're going to be sending your spin variables you're going to be switching signs on your spin variables. And one of the old theorems in quantum mechanics is to do that in general, you need anti-linear operators, right? And so your A is actually not entirely general because it would be a linear operator in that form. Is that correct or not correct?
Why does it have to be, sorry, why does it become nonlinear?
Well, anti-linear.
But where does that come from?
So for example, if I have an operator that flips Z, X, and Y to negative Z, X, and Y, I believe that you would need to do that with an anti-linear.
Oh, right. So indeed, so if you're talking about like you have Z which or X like just flip a spin, well, quantumly it becomes a Poly operator. So it's not like you actually send like plus Y to minus Y and like so there are lots of choices of jump operators.
Okay.
Is this in this analogy between bit strings and eigenstates, eigenstates are fundamentally very different technical objects.
Exactly. That's why this idea wouldn't exactly work out. But this is kind of intuitive.
But is this kind of the only systematic way to try to quantize this? Because this creates a huge amount of complexity with these eigenstates.
Yeah. So indeed, to echo with that, eigenstates are really delicate objects. It's very complex. It's hard to access. That's why initial attempts has not been perfect. So we'll try to do as much as possible along this line, but of course, have to technically change lots of things. But this is roughly a guiding principle. Yeah, so there's lots of fun challenges, kind of if you want to go along this route. The first one is algorithmic. The challenge here is how are you going to coherently reject a state without collapsing it? Right, so classically, you can, if you want to do rejection sampling, you can just go and then sometimes reject it. You can just undo the jump. Or you can even just clone a state. Right, you have lots of things you can do to achieve this. But quantumly, this is not so obvious. Right, you cannot clone a state. you might have to be very careful with your measurements. Otherwise, you might collapse the state. Okay. So this is reminiscent of the task or the algorithm of rewinding that people I think have still been discussing recently. So you have to do that, and that was quite a complicated algorithm. The second challenge is analytic. It's precisely that energy measurements is always kind of difficult. It's very difficult to access energy eigenstates, and same as the energy measurements. So you can think of that whenever you're running this Markov chain, your energy estimates are going to be like uncertain, like fuzzy. And you can imagine how this is going to change detail balance. And detail balance is something that we have lost so much in Markov chains that if you lose it, we're kind of very unhappy. As of today, these two challenges have been kind of avoiding lots of previous attacks of Gibbs sampling. That's kind of why this problem is hard. Okay, so today's algorithm, we overcome these two challenges, and here's what we got. So the algorithm looked like this. It's a continuous time Markov chain. If you like discrete things, this is maybe not kind of entirely familiar, but this is what we constructed. We claim that our algorithm satisfies the following criteria of a Monte Carlo style algorithm. It is efficient in the sense that this exponential can be implemented efficiently. There's a quantum algorithm for it. And second, it has the desired property that it fixes the Gibbs state. Right, so with the first two, it's very similar to the classical case. And you can now run this algorithm on a quantum computer and see what happens. Right, if it converges quickly, you win. If it converges slowly, well, maybe you have to try another algorithm. In either cases, even if you don't know the mixing time, you can still write down the cost per Gibbs sample. It's going to be a cost of implementing this one step. And it's going to be multiplied by the mixing time. It's like how long you're going to run it. It's very intuitive. What's interesting here is that all the complexity essentially boils down to this mixing time, which seems to be a quantity that in quantum computation has not been quite discussed. Right, so I know some of you don't like continuous things, so I will spend a slide discussing what this continuous time Markov chain is. You can think of it as a continuous quantum version of a continuous time classical Markov chain. So it's like a generator. So it's not like a discrete map, but rather it gives like tiny changes. So you have to take derivatives. Quantumly, it has this form that some mathematicians have just worked out the explicit form. It looks like this. It's entirely parameterized by a set of L's. Okay. And any of L would give a valid of continuous time quantum Markov chains. You can think of this as a continuous version of quantum channels. So these L's are just analogs of cross operators. But because it's continuous, you kind of have to add this second term to make it trace preserving. But other than it's not too different.
So related to the continuous and quantum.
Is it coherent or not?
It should be. I mean, you can make it before.
But this one is usually not coherent. So yeah, you're working on the density operator.
You also don't have the I.
Right, you're just directly working on the density operator. So there is some classicalness in it.
So this is a generalization of continuous and classical walks.
Yes.
And we don't know how to do that for discrete case. That's what you're saying?
The discrete case for the quantum.
Yes.
Yeah, that seems hard, and this one seems to be much easier. Even though it looks kind of scary, but somehow this is much nicer to think about.
Sorry, I missed that. What was the statement that you can't do in discrete time that you can in continuous time?
Right, so the task is to do Gibbs sampling, and you can do it discretely or continuously. And now I don't know how to do the discrete one, even though we know how to do the continuous one.
Sorry, can't you just unravel the quantum walk and discretize?
Yeah, but you're still basically working on this guy.
Yes, but you can discretize that in time. Converge to some extent. So.
Yeah, but you still technically you still think about this object. Because I mean, in Metropolis, you kind of have to do this discrete rejection. I just said I don't know how to do that. Still.
So you wouldn't call it a kind of trotterization of the discrete equation?
I wouldn't call it, yeah, but you can do it.
Because it doesn't have a kind of a discrete rejection. Yeah.
So the issue you have with discretization is detail balance, isn't it? So if you were to try to discretize this, would you lose track of how to maintain detail balance?
So I don't even know how to construct a map.
And also the rejection. I mean, everything would have to be approximate.
Yeah.
But I mean, you could just discretize it and put in all the epsilons and deltas and you get a discrete kind of process that would just...
Yes, exactly. That's exactly right.
It's just that's not what you're
that's not what I was talking about. Yeah.
So on the previous slide, you mentioned that we have that your result is that we have an algorithm that satisfies the top two checklists. But I don't get how different is this from the state of affairs when you just or is that the algorithm?
Right. So you can think of this as a way of algorithmically imitating the path, of extracting all the essential functionality of the path.
And okay, so it's sort of the same, I guess, lack of clarity about what the mixing time is as.
Yes. So mixing time is always hard, and it's similar to the classical case. In some cases you can prove it, but in many cases you just don't know, just try.
But I mean, I could also just simulate the path by doing this larger Hilbert space thing, right?
Yeah. So indeed, so you can just say, well, I know the physicists have been doing the right thing. Let me just quantum simulate the whole lab, right? But it requires the path can be really large. Sample usually is quite small and the path is really large. So if you want to do that, it works, but it's quite expensive. But the point here is that you really just distill the thing you want and reduce it to a very few set of incidents.
Okay. That's the main result.
That's the main point.
Yeah, let's take
So you have a question. So in classical Monte Carlo, if you talk to practitioners, so that actually use this, they don't want to simulate the bath at all. They say that this doesn't work because like you want to cool down and see what kind of crystal will come out of something. You want to do completely unphysical moves, and if they do this, they get like 10 orders of magnitude increase in speed as opposed to simulating the bath. So
exactly.
So that seems to be like a reason why you don't want to do what you want to do.
Yeah. So it depends on what you want. If you just want to simulate what physicists see, then you can say, well, let's just try to simulate the whole path. I don't care about Gibbs state because I just want to imitate what they're doing. You can also just say, I want a Gibbs state. What's the best way of doing it? I take inspiration from nature, but I upgrade it.
Yes.
Yeah. And you could just get that like much better.
Okay, but I understood that you said that you want to do simulate the bath. That your effectively opinion is like the bath, simulate the bath.
All right, we take inspiration. We take inspiration from that. Like today, the goal is to get a Gibbs state, not to simulate the path. Simulate the path is like it seems to be working, so we borrow it and improve it.
I think the point is that you have control of what's invariant you're choosing. Because you could choose an invariant that represents the interaction with the physical path. But you could do other things.
The whole the people that use this, they have to do very non-local moves, and only then does it work.
You can also include.
Moves that you can't even model with a
Yeah, that's it. That's what I. So you have to do very non-local things, and
You could include that in the.
Yeah, you can do that. You can do that. Yeah.
Maybe a quick question. Is your invariant non-local? Do you
That depends on the problem. But I will show a slide that in some cases is possible. Right, so in Darlin, and we've been discussing it, and also nice discussions. So when we design an algorithm, our goal is to basically pick the right set of Lindbladian operators. And it's been like, right now it's not very obvious why this have all nice properties, but it is your task as a designer of algorithm to pick the right one. So here's the main result of today. It's the most technical slide. Today we present the quantum version of classical Markov chains, or quantum Gibbs sampler. Here's a statement. For any Hamiltonian, on n qubits and any desirable choice of temperature, inverse temperature beta, and some set of jumps. Okay, so given that, we construct a Lindbladian L, which is a continuous time quantum walk, quantum Markov chain, with the following desirable properties. First, the Gibbs state is stationary.
Is it the only stationary state? I'm sorry.
We don't know. We don't know.
That's super important. I imagine you have an exponential number of stationary states.
So that would be bad. But we don't have a quantum computer yet. So it's a question that now we can answer it on, say, 10 qubits by doing numerics.
And the numerics suggest it's unique or not?
Or just,
what does the numerics suggest? That it's unique?
In some cases, it's fairly unique. Sometimes you have 4 different fixed points. So yeah, lots of things are happening, and we haven't quite know what is, because it's all new. We don't have experience.
Uniqueness. Sorry, I mean this is uniqueness is a binary property. So something being fairly unique, I don't know what that means.
Oh, it could be like the Lindbladian gap is very small. So if you wait a long time, they actually die this way. But if you wait only for a short time, they're like several metastable states.
But there is a quantum version of detailed balance. No, you can use.
Yeah, that's what we're using. That's what we're using.
Balance equation.
That's how we design the algorithm.
But that is unique. If it's ergodic and it satisfies detailed balance, it's unique.
Yeah, but ergodic is, we don't know how to always make it ergodic. Okay. Yeah.
So what's the relationship between the jumps and the Lindbladian?
Right, I think so in classical, you choose a set of jumps, and out of those jumps, you construct a Markov chain.
Right.
And so it's a parameter of the algorithm. And if you choose the wrong jumps incorrectly, then you might just not able to traverse the landscape in some sense. But it's something that would go into the Lindbladian. The Lindbladian depends on this jump.
So it's sort of implementing those jumps in some way, essentially.
Yeah, it would take a jump and then dress it by some quantum algorithm, and then to get your Lindbladian. So it's kind of complicated. It depends on the previous things in a convoluted way.
I'm just confused about the uniqueness because, I mean, if you just wanted to satisfy this theorem, you could just do nothing.
Yeah, I don't want to do that.
Yeah, so you probably have more stringent conditions than just the Gibbs state.
Right, but if you give me a particle Hamiltonian on lattice, you would naturally choose a jump to be single-side flips, or maybe like 2-body flips. So there's some classical, I mean, you can kind of borrow what people did in classical and then try to just do it here. But indeed, I mean, this is, you can have lots of like worst case example where this is true, but the thing is like not the right thing to do. But we do have a construction, and I think in numerics it seems to at least not doing like completely stupid things. So.
Is the right way to think about the required t that is probably some increasing function of beta? So if I wanted to just write the simulation time only as a function of beta, it would be superlinear, but we don't know what it is.
Yeah, so based on classical intuition, if you want to go very low temperature, it usually gets harder. But it says when beta gets large, it usually gets harder. Sometimes it gets really, really hard. Sometimes it doesn't increase as fast as SOKC. So it just depends on the case. But in general, low temperature is harder.
Okay, just check I've understood. So this efficiency doesn't mean efficiency because there's a mixing time hidden there, right?
After
This is,
mixing.
you're simulating the Lindbladian, but
For
you
one
have no idea if that gets close to the
Exactly. Just think about Monte Carlo. Like people don't know how long it's going to mix, but each step is efficient.
Yeah. So if your local operator satisfies some assumptions, can you show it as a point?
Yes. I haven't thought about that too carefully.
Okay. So for example, if you satisfy like ETH type assumption.
Well, I think ETH then probably yes. ETH is very strong assumption. So ETH, by the way, is some physics assumption that make your life very much easier. But mathematically, it's not solved. Right, and go on to the second condition, which is that you can efficiently simulate Lagrangian, and here the cost. Right, it only takes very few resettable ancillas, and a Hamiltonian simulation time that scale with T and beta. Okay, so let's try to understand what this means. It only needs very few ancillas, which means that you can replace a whole big bath by a few things that you can control. Okay, that's what this algorithm achieves. And this Hamiltonian simulation time scaling, T and beta, we think it's essentially optimal, because individually it's optimal for either T or beta. And it seems very hard to get beyond this product.
Right, I guess, can I ask about that? Like if I know what the mixing time is, are you saying that preparing the Gibbs state is probably optimal in P and beta, or that simulating?
Yeah. Right, so here I don't care about mixing time. It's just like this black box problem.
Okay.
Simulate and Lagrangian.
Okay. Thanks.
So this is the main result, but there are lots of ones I haven't had time to show you. In our paper, we basically established a lot of frameworks to analyze this, which directly applies to other problems, such as other Lagrangians coming from the system path. So it's like a physical setup. We also can prove similar results. And the more algorithmic side result is that we also be able to produce the purified Gibbs state. So the whole thing becomes very quantum. So it's like another layer of quantization. And you can get this purified Gibbs state in your quantum memory. So let's try to get an intuitive understanding of what's going on. It's very similar to a random walk. So if you go to energy basis, you can think of some blob of probabilities that's being moved around. But because of energy uncertainty, there's some coherences at nearby energies, because you can't distinguish them. So it could just remain coherent. Okay. But there are two effects of mixing. One of them is incoherent, which is more classical. You're moving things around. But there also is coherent mixing, that because we cannot distinguish energy. And so you see they're both classical and quantum effects. That's driving the Markov chain, which make it interesting. Nevertheless, we enforce detailed balance so that the fixed point is still the Gibbs state.
Sorry, can you explain what's coherent mixing?
All right, so when you apply these jumps, it may not increase entropy. You could just rotate the states around. There are parts that could increase entropy, because there are parts that don't. So this is just intended to be very intuitive. So if you look at our generator at the space domain, it's actually very nice. So let's consider a lattice Hamiltonian with single side jumps. Okay. Then our algorithm actually simplifies to a sum of local invariants, where each individually fix the Gibbs state, while at the same time they're all local. And the size of these jumps is just beta. In other words, if you want constant temperature Gibbs state, this is locally Lagrangian that gives you the Gibbs state as a fixed point.
What's the intuition of a local invariant term which preserves the Gibbs state? Find the sum of any two. Because I mean, it's a global property to be the Gibbs state, not a local property.
So can you repeat the question?
Right. So the question is, what do I mean by these things preserve the Gibbs state? So it's just this equation. So if you fit in a Gibbs state and you act on this, the Gibbs state is annihilated. There could be a lot of other states that also.
I understand what you mean by this. Yeah. I find it very unintuitive. So I was asking if there's some intuition, because being in a Gibbs state is not a local property somehow, right?
Yeah. So the intuition is that detailed balance can be implemented locally.
It's like saying it's frustration free.
Exactly.
That's how it sounds to me, which is like
exactly.
Case.
Exactly.
Are you listening? Oh, sorry, it's frustration free.
Yeah, frustration free. Yeah, exactly. Yeah.
So does this require interactions?
Yes. Just use a Lycon argument.
What does frustration free mean?
Yes.
I'm sorry.
I mean, so every Lindbladian jumps fixes
That's
it.
the definition of frustration.
But I'm just importing the intuitive meaning of this in the Hamiltonian case and put it here.
We have examples of frustration free in that sense, which are not convoluted.
I think so. Yeah, I think so.
You have examples?
I think people just write down this all the time.
No, I mean, when I hear frustration free, it's a property of the counting alone, right? So we might have a station.
All right. So to be very
That's
precise,
what I'm wondering.
you can view this Lindbladian as an operator. So it's a super operator. We can just say, well, it's still a linear operator. Then the Gibbs state is actually the ground state of that operator.
I think you have two types of
You have
locality.
to check out the properties now when you do this mapping. I mean, it's not positive or anything.
Right. So you actually have to make it. You have to take the discriminant. You have to do a similarity transformation. Then it becomes like Hermitian.
Yeah, but what I know is that there's examples of frustration. I mean, sorry, but there's examples of frustration from two states, and then you have to find a way to map these back to density operators, right? And which are thermal states of local Hamiltonians. And that's completely unclear how that actually works, right?
Yeah, I think
I
that's
find an example of a frustration-free Hamiltonian, which is not uncountable. You think Hamiltonian by this mapping will give you a thermal state of a local Hamiltonian. I mean,
Right. So that's why this is interesting. I guess this whole frustration free and local all comes out. And this is a realization we have.
Again, we have examples which are not computing. To me, it sounds like it means that it has to be computing.
No, they're not going to be. So if you take our construction of Lindbladian, it has this property. So it's a very general construction. They always have this.
Okay.
So to be clear, for any Hamiltonian, you
That's
go
local.
through your construction, it will have and construct a local Lindbladian that will have this property.
Yes. So given that is Hamiltonian and local jumps, this is required a Lycon argument.
I guess you have two types of locality, and one is the local jump, which is a truly local,
Yeah.
and the other types of locality is through the Lycon, which can be
Yes. So both of
local-ish,
them.
but it's much larger.
Yes. You need both.
So how large is support? Does it depend on your energy resolution?
The energy resolution is roughly beta, or inverse beta.
Okay. So it's basically the radius is linear in the energy resolution.
Yes. Which makes sense.
You're going to give an explicit construction, right? It's
Depends on the time. I might try to skip those. I don't. Even if I go through them, I don't say too much on those sides because it's just kind of technical.
so okay. So for example,
I would suggest not skipping it.
Okay.
People want to skip out.
Okay. Yeah. So in that case, I'll go through the construction a little bit. Maybe it was not satisfy you, but that's some of it.
So according to the picture, it seems that different states are connected with each other. And why you're not computing is not allocated?
It depends on the choice of jump.
So can you give some insight about in what situation your marker changes?
I haven't thought about it.
So I have another question more physical, right? So if you look at the relaxation in the heat maps, right? It's not first principle. So if you use latitude simulation, that's fine. But if you use latitude real physical implementation, you draw a physical state from, say, Gibbs distribution. I'm not even sure, you emulate that relaxation process will work in reality. Because if you just look at thermodynamics, right, it's not first principle.
Right. So I don't have data to explain the question. Explain your question. Like you can say, oh, when I'm running this artificial algorithm, how does it compare to things actually happen in nature? It's not clear. It could be different.
That's right.
Is that what you're?
That's right.
Yeah.
That's right.
It could be.
So it's not a lot of work, not a lot of work in real system. Even if you emulate perfectly a relaxation, you make it fast.
Yeah. I mean, this is all just models. I mean, we're trying to write out something that's going to make mathematical sense and capture as much as possible of the model. But the model could be very dirty.
So the other question is that the convergence is more asymptotic. Do you have any finite time analysis about it? Say you have a distribution, right? It's not a perfect distribution. For example, you only run this, right? If you run this for time t, how far you to the Gibbs distribution? Have any analysis?
Right. You can ask like, oh, can I just get something that behaves like a Gibbs state, but it's not actually a Gibbs state? That could happen. There are all sorts of ways to approximate this algorithm. What kind of relax the thing you want. Like if you really want a Gibbs state in like trace distance, this is kind of how we set up, but you can relax this in many ways. Okay. All right, so let me just add one comment. I know lots of people really love ground state. They don't like thermal state as much. So you can also apply this for ground states if it's gapped. And the cost just amounts to setting this beta to be 1 over the gap. And there might be log dependencies. So the intuition here is that in order to know that you're getting lower energy, and in particular that you're going to the ground state, you sort of need to resolve the energy scale of the gap. And that's kind of all you need to pay. So that this 1 over gap is going to enlarge each of these blobs of Lagrangians.
There should be a log n factor. No?
Yeah, I dropped those in this omega tilde here. Yeah. So in complexity, log n is quite important, but just physically, I think just put it here too. The emphasis only depend physically on the gap.
It's a comment that I was going to make to Dorit earlier. It's not enough to just, you can have gapped, constant gap is still NP hard. So it's not just a gap that matters, it's also
mixing time. Yeah, right.
The mixing time, exactly.
Right, the mixing time and the density of states. So here the reason why you actually get a log n factor is because the very excited state, there are like n of them usually. And if there are more of them, well then,
which is what happens.
I suppose, yeah, okay. Then this will have to change.
Yeah, I was just talking about state preparation, not about mixing.
Even state preparation, same problem.
No, state preparation is not classical. I mean,
No,
if you have a gap Hamiltonian, then you can prepare it if you have a constant inner product with your graph. In case of classical, quantumly it does.
To prepare it with a constant overlap, though, I mean, with phase estimation, density of states matters.
No, once you prepare it,
Yes.
then you can do it. That's what I said. Yeah. We're all waiting for the question.
So most systems, if you cool them down, get symmetry breaking. You know, they
Oh, right. Right. So for example, if you just take classical Ising model, and it has basically of this all up and all down, the mixing type explodes. So you don't get a Gibbs state. Yeah, and it happens. And then at the time, you might just change your goal. You say, oh, I just want one of them, then it still works. Does that answer the question? But if you have lots of symmetry, then it could be lots of states that has stationary, that has the stationary, that will be the fixed point. And that's fine. It's a feature of the model. You can try to break it by choosing an appropriate set of transition that break the symmetry. Then it would change. So lots of like different situations.
But for this, you need discrete updates, not continuous.
I haven't looked at it in full detail, but I believe the symmetry argument will also apply in this sense. Okay. So that was the claim of the theorem. Now let me try to explain why it is supposed to be powerful. What's new here? So the secret sauce of our recipe is continuous rewinding. Okay. So it appears that instead of doing discrete rejection, which have been discussed with the audience, somehow doing this continuously just make your life 100 times better. Like really, 100 is like actual thing. It just makes everything possible. I think it make the map like possible to be presented, to discuss. And yeah, and so somehow when you do it, it becomes even more simpler. So like on the left hand side, you have to go back, and you first go there, and then you try to go kick it back, and there are all sorts of epsilons and delta that make you miserable. But here, what you instead do is to just weight the continuous transitions. So if there could be many different jumps, and you just want to put different weights on it. And if the one that you don't like, you put a very small weight. The ones that you like, you pick a very big weight. And it effectively is doing rejection continuously. And it's common that nature seems to be doing this by system-based interaction. Because nature is continuous. Can also justify why this seems to be nice. But algorithmically, to really do this, you have to use a lot of tricks, like of course, like QFT, Hamiltonian simulation, and some weak measurements. And this weak measurement is especially for doing continuous jumps.
Sorry, there's something I don't understand. So in the discrete case, one can also think about putting weights there, except that to decide the weight, you have to know both endpoints, right? Which is why you jump to it. You know, quantumly, you don't just decide the weight. You've got to know what your other endpoint. You don't know you jump to it.
Yes.
So how do you do that in the continuous case without knowing what that endpoint is? Without jumping. You know, so that
yeah. I actually don't have a very good explanation. Is that somehow the embodying formalism just becomes extremely direct. So you just write down a set of the embodying operator and then say, oh, I want this to have this coefficient. And then there's like black box embodying simulation that allows you to do this. So I don't have to have a very nice intuitive explanation. It just seems that when you do rejection, there's so many complicated things that come out of it. So it's not understanding that. So. Also, I want to give an explanation of why this is powerful. So in this three-level example, where the Hamiltonian has 0, +1, and -1. And let's suppose we do a jump A that maps to +1 and -1. And let's see what's going to happen in our algorithm if we implement this. In average, the Hamiltonian energies actually doesn't change. However, there's part of transition that increase the energy, and also the one that.
What's your Hamiltonian here?
Let's just say you have three-level 0, +1. Yeah, Hamiltonian is diagonal with three states. Okay. Yeah, and then if you apply algorithm, what's going to do is to punish this transition that's going upwards. And it's going to favor the transition going downwards. So then it actually realizes certain kind of Hamiltonian gradient descents that you don't get to go up, but you can go down. And it would just have this transition going down, and if you wait a while, it becomes the -1 state. Remarkably, this does not require any post-selection. This is really the power of rewinding. Because whenever the state wants to go up, say no, stay there. Some of these idling make it very, very nice. So in other words, you can actually repeat this process if you have Hamiltonian have lots of levels. You're not losing any probability, so you just keep going down and going down. But there's no hidden exponential factor in these algorithms.
And just in the context of this slide, so are you saying that this is the idea underlying what you're doing, or?
Yeah, this is to illustrate what happens if you run an algorithm with a Hamiltonian that has 3 levels, and a jump that does this. And just illustrate how the energy gets lower. It's because it put punishment on increasing energy and favors the decreasing.
This is the
At
gradient.
this level, this is also what the Metropolis algorithm would have done.
Yes, because it's all discrete. So this you can actually do this discrete.
So this is the gradient of
H with respect to A, kind of.
H with respect to
So to talk about gradient, you want to choose the objective function, which is Hamiltonian. And now you're changing things according to A. And our algorithm isolates the transition that decrease the energy with respect to Hamiltonian.
How to see that this is the gradient of that?
Okay, this is just some words I described. But, so this is what I meant.
So is it possible to give an example of the construction for this example?
You can take the Hamiltonian to be 3 level and then A2.
No, the Lagrange. The construct. Yeah.
Yeah. You can. Yeah.
Can you do it now? Like, I mean, I'm eager to see the construction in some way because it's very abstract.
I think the point is the suspense is killing us all.
Yes.
Okay.
So either for this example or in general, can you show us what the algorithms are?
Okay. I can just go there maybe.
This is a classical example, isn't it? Or which aspect of this example is
Right, so to make it really quantum, you can make the energy levels like really continuous. Great. So let me choose the wrong example. Let me just keep going then. Right, so here's unfortunately another classical Hamiltonian. That illustrates at least what this is doing. Is that the fact that it's preserving probability save you from lots of problem. So suppose you want to prepare the ground state of this guy, the classical Hamiltonian. It's all 0. And you start with the initial state that has little overlap. Right, so this overlap is something that people have constantly discussed. And if you just do imaginary time evolution, this actually kills the algorithm because the overlap is so small. However, because our algorithm preserves probability, it only takes a very short mixing time to get to the ground state. So you immediately see that there's some qualitative difference happening.
I think at this point, understanding the algorithm is much more than.
Okay. So let me. Okay, so here. Right. So what are these L's? Okay, what are these L's? So here it is. We're going to isolate transition by the energy changes. If energy increase, reduce. If energy decrease, enhance. So we would choose this invariant operator to be something look like this. So it's some scalar times a matrix. These will be a collection of all invariant operators. All right. So what is this A? This A is right. So what is A is some matrix that has some matrix, and then we look at it at the energy basis. So there's like a matrix. So here are psi I and psi j, 2 different axes, and then there are going to be lots of entries. And what you want to do here is to select only the transitions with energy difference omega. So you start with the matrix, could be really large, but you just cut out everything else and just keep this tiny band.
So this is a way to select the eighth?
No, this is the way to construct A omega out of A.
So you're given a set of jumps, A?
Yes.
And now you're constructing
A filtered version of A.
Okay.
Which throw away lots of transitions. And the reason why we do this is that all of these have very similar energy changes.
But they're all very non-local.
They're awfully non-local, exactly. Well, depends on how precise you want to be. So there's actually like an energy window you can choose, like the resolution. If the resolution is very, very good, it's really non-local. But if it's not perfect, it actually could still be local.
And how can you efficiently construct those?
So that will be the next slide. Yeah. But in energy picture, it's very clear that, okay, you want the jump to change energy by this amount, omega. And once you have this, assuming you have this, you just multiply by the appropriate weights.
Sorry, but in all this, if you had a way of identifying the energy precisely, then you would have done the discrete thing as well.
You could have done the discrete thing.
So somewhere in here, you're going to say why this gets around the non.
Yes. Yeah, so the very technical thing is that there's this uncertainty omega. Uncertainty, like some window of uncertainty. And then that makes discrete rejection like awful. But here, if you just look at this guy and then just plug into Lindbladian, it defines a Lindbladian. And it doesn't have to think about rejection anymore. You just have a Lindbladian, you just have to simulate.
But in the construction, you're happy with delta being a constant or a fixed thing.
Like
It's not,
beta.
you're not taking it to, so it's
Yeah.
it's of the order
It's
of beta,
not too big. Yeah.
and you're not taking it to zeta.
No.
So you don't get the Gibbs state in the end, but something.
We still get a Gibbs state. That's the remarkable thing.
Oh.
So the point is that Gibbs state is actually kind of smooth. The smoothness of Gibbs state is roughly beta. And that's kind of all that you need to pay here.
So you get exactly the Gibbs state or approximately?
Like very high precision approximation. It's like log epsilon, like log epsilon.
You're saying it's exact, right?
It's effectively exact. In quantum algorithms, all algorithms usually have. You always get log epsilon dependent. So it's not 1 over epsilon, but log epsilon. So it's effectively there.
So where are the gammas coming from?
You choose them.
Oh.
Right, because you first have these kind of very quantum objects, and then you can, when you know the energy, you can just apply like classic kind of like weight, just control weights on it. You can choose them. You just need to have detailed bands. Right. So how do you actually implement these like highly non-local, like so this weird physical thing that you directly address the energy basis? It actually has a very simple time domain representation. It's just a Fourier transform, as we always need in quantum algorithms. So what is this A of t? It's a Heisenberg evolution of the operator A. So it looks like this. This is actually something that's very physical. It shows up in physics every day. And then if you write it out, it actually just naturally has this exponential ei minus ej expression. Because on one side you have plus h, on the other side you have negative h. And then naturally diagnoses how the energy is changing.
So you're working in the energy basis.
Yes.
How do I get those energy states in practice?
All right, so this is a way of representing the matrix. But this is the one that you actually implement. This is perfectly physical.
Okay.
Where A is no.
The A is some simple operator like single Pauli's. And you sandwich it with Hamiltonian evolution.
So Heisenberg evolved that.
There's algorithm to like implement this H.
But then you have to average on T.
Right, so you need some circuits. So it's next slide. So actually have to do something look like this. So you have two-sided control Hamiltonian evolution. You put some weights and you do a Fourier transform. So it's in some sense not too different from phase estimation, but I mean it has this similar kind of ingredients. But it's appeared to be the right way of doing it.
But how is this different than this quantum metropolis sampling? Because that's exactly the same thing then.
Well, I mean, there's lots of technical differences that make the algorithm different. But intuitively, yeah, you're just measuring energies and then put the weights at the right kind of energy trend. Like intuitive is similar, but technically, to implement this we actually take a lot of time to think about this.
So what goes wrong in the Metropolis algorithm is that it doesn't, so where does it differentiate, not technically, but in terms of, if you try to do the other description, what happens? What's the problem there?
So there's one very technical assumption that we find to be impossible, but maybe they can just change the technical assumption and it still work. Like they assume some very like superpower version of phase estimation.
Super powerful?
Like yeah, so there's some physical version of phase estimation. And then like maybe you can remove that and it still make the algorithm work, but now we don't know how to do it.
Like with extreme accuracy or something like that?
With extreme boosting.
Sorry, what do you mean by extreme boosting?
Oh, like it's kind of related to rounding. Is that if the energy is something between two mesh points, then there's some non-boosted parts. you can have something that's highly precise in bands of energies, but not in the cross points. Yeah. So it could be a technical problem that could be solved. But.
So is it possible to give an example before this slide? Is it possible to give an example, like take this and show how the very simple walk that you give an example of 0, 1, 2, or 1 minus 1, 0. Is it possible to show how this looks in this case?
Well, this A omega would just be selecting the transition. So if you care, so this A minus would be just one of the jumps, one of the A omegas. Because this has energy difference -1, you select that thing, and then put a weight on that transition.
Sorry, the A minus is already, you don't have to do the filtering there?
When you start with A and do the filtering, you get A plus and A minus.
Oh.
Yeah.
Because it's discrete.
Yeah, because it's discrete, you can very simply talk about this. But if it's continuous, well, things got fuzzy again.
So basically, in this case, you just start with a single jump, and then you get two I don't know,
incoherence
jumps or whatever you call it, and that's what you're using.
Yeah. Right, so it's very important that you can kind of incoherently address both of them. Right, then you can say, I don't want this part, I want this part. And you can do it.
If you take this prescription and do it for a classical walk, for a classical continuous walk, then you get the natural thing.
You could, if you choose everything correctly. I think if you have like a combinatorial problem, like all these is a Hamiltonian, and you only flip x, then it reduces the classical case if you start with an entangled state. But if you start with an entangled state, no one knows what happens. We don't know if there could be like speed ups. We don't know.
Could you go back one slide? Yeah, so the A's you choose in order to that you put in the circuit there, are they related to the local jumps that you start off with?
Oh, you just A? Yeah, you would choose that. Right? So it could be single poly X, and you run this and you get the filter version.
And you get the weights that you require for detailed balance based on the omega register.
Right. So there's a control omega, and you put some control weights here.
So you coherently compute the weight
Exactly.
with another circuit.
Exactly. Yeah.
So you synthesize the other Metropolis objects because you have like only finite energy. You could only measure energies up a certain precision, but it seems that you have the same problem here.
Oh, right. So here, you can actually make this infinitely. You can actually put a lot of energy register here. So this omega bar is actually like only an energy proxy. So so this is kind of very technical, but what resets your resolution is the Hamiltonian simulation. You can have like a continuous representation of this omega, but each of them is smeared out. So there are actually two different energies we're talking about. So if you look at this picture, you can have a continuous omega that's scrolling around. However, there's this energy uncertainty. So if you only change omega by a little bit, this operator doesn't change that much. So the fundamental resolution is this parameter, but not how many omegas you choose. It is a little technical, but this goes into it. Yeah.
And in simple cases, you do get Gibbs states, or?
You mean like in numerics?
I don't know. When you try simple situations, do you get the usual?
I haven't tried.
You did.
I haven't tried. In numerics, we see that it could be like 4 metastable states, but if you wait a little longer, they all collapse to the Gibbs state. Because in small systems, I think everything is quite unique. Generic.
Try to understand what spoils uniqueness here.
Oh, uniqueness just refers like whether there's only one stationary state.
Yeah, I know. Like
What spoils it?
what spoils it?
Ruin.
Symmetry is one possibility. Or if the system is actually very glassy, there are lots of it's hard to traverse the landscape. And then because the mixing time is really long. Because you can have actually unique stationary state, but lots of states that have a very small gap. So it takes a really long time for them to mix.
So
either
formally it's
or,
still unique, but you just have other.
It's physically not unique. Okay. We're all hungry. Right, so let me just quickly summarize. Today we did an algorithm that prepares a Gibbs state in Monte Carlo fashion. It satisfies the two desirable features of Monte Carlo. That's efficient and correct. And I have not talked too much about this uniqueness, but in practice it's quite important. And the cost is just go with the mixing time. Okay, so let me end with opportunities for those who are still interested in this topic. So in classical Monte Carlo, ever since its invention, there have been so much research in the past few decades. And here, I argue that we're in some similar positions, because now you have this quantum Markov chain. You can ask all sorts of questions that people ask classically. You can ask about mixing times. You can ask what happens if I apply to an optimization problem. How does algorithm compare to existing algorithm? There is so many things that we don't understand. Now we're just doing like very small scale numerics and see what's going on. It already have some nice kind of scientific understanding. And I would like to end just by saying that, well, maybe Gibbs sampling could be the first useful quantum algorithm, because it seems like quantum simulation really requires this initial state preparation. So maybe this could be really useful as well. And thanks for staying. Yeah.
Everyone's hungry. Here's a question. You just look out.
Yeah, sure. So can you generalize this to some other type of stochastic matrix, like a double or triple stochastic matrix, or hypermatrix form?
Oh, do you mean the quantum one?
Any of them. Can you actually generalize this to like some other type of stochastic matrix, such as double or triple stochastic or hyperstochastic hypermatrix?
Oh, you mean to extend detailed balance? But like, I guess so. So indeed, detailed balance in the classical case is not a unique way to get like Gibbs states. But I haven't thought too deeply about that. But now we just use detailed balance. It's somehow nice to understand.
Sure. I have another question. Yeah. So like, does this generalize well? Can you conjecture or like provide intuition as a comment on whether or not if the bath was a Q-trip spin glass or a Q-trip spin ice? Does this generalize well to that?
Oh, so if you want to make your bath kind of more exotic, I don't know if this would apply, because usually in an open system, people just assume the bath is extremely nice, like almost solvable and like all sorts of like bath properties. If you change the bath, I think it becomes an independent problem.
Okay.
Use of the word, the first useful, deliberately chosen to be provocative.
Yeah, this is like hopeful, this is the end with something cool.
Because this construction uses Hamiltonian simulation. Presumably, Hamiltonian simulation.
But some variant of Gibbs sampling. There's some extremely simplified version of Gibbs sampling.
So thank you for your talk. It was very interesting. I was just going to ask you if you do happen to work out an example, okay, even the example you showed, I I'm going to be here for a couple more weeks. I think other people would also want to see it. And it might be interesting to just give the talk in a way where you're focusing on that example.
The details.
Yeah, because it was a little bit hard for me to understand what you're actually, you know,
Yeah,
at all points. So if you're around, I'd love to see it. I think some other people would. It could be kind of interesting for us to.
That could be fun.
You know, going on to what he was saying with this first quantum algorithm, it'll give you an opportunity maybe to count the resources if you write down these circuits.
Potentially, yes. Because all of these are ongoing, so I apologize because we're trying to distill. You know, we start from some 50-page paper and try to like make it simpler and simpler, and only in the middle. So, yeah. So thanks again for bearing with me. Ongoing.
Thank you. We'll still reconvene at 2:30 if the dates that are kind of close by. Be a little slack line. Is that okay?
Perfect time.
What?
Perfect time.
Quickly, 2 o'clock.